Welcome to the Microchip Is podcast. Join your host, Mike Maynard, as he learns about the technologies, products, and people that make microchip technology what it is today.
Welcome to the Microchip Is podcast. Today, I'm talking to Perry Schugart. Perry is the head of marketing for the SiC business unit at Microchip, and I'm going to find out a bit more about Microchip in the world of silicon carbide. Hi, Perry. Welcome to the podcast.
Thanks, Mike. It's great to be here.
So to start off with, Perry, can you just tell me a little bit more about your role at Microchip?
Yeah, so I'm responsible for the marketing in the silicon carbide business unit. That includes all outbound marketing, product management, product marketing, R&D roadmaps, basically anything that has to do with our product portfolio.
And that's great. And silicon carbide, or SiC, is generating a lot of excitement at the moment. Can you explain a little bit about that technology and how that's different from conventional silicon chips?
Yeah, so it's a great question. A lot of people ask, why now? What is SiC? Silicon carbide is known as a wide bandgap material. Not to go into too much detail, but what you get is the ability to switch much faster than silicon. Also, you can build die with lower RDS on, and you can go to much higher voltages. So when you look at opportunities like where efficiency is key, or high temperature, or size, this is ideal for silicon carbide. And what's really driving it is the electrification of everything. I think of it like the Internet of Things was, where everything's going to be connected digitally. Now we're seeing it happen in power. Things are connected hardwired, or they're connected wirelessly. We're seeing wireless charging of EVs. So that's created a demand for new applications. And the other thing that's happening is loads are becoming more sensitive. So there's a higher need for control. And with a device that can switch much faster, that gives you the opportunity to do things you really couldn't do in silicon. So, as an example, you can think of like power steering in a car. That used to be hydraulic. Now it's being electrified. You can think of new applications like the eVTOL or the air taxi that didn't exist before. And these are ideal for silicon carbide, where silicon carbide can give you a smaller system. It can go to higher temperature. It's more efficient. And, that's just a few of the applications that are driving this need.
And that's interesting because it sounds like there's a couple of things going on there. I mean, one is the electrical characteristics, the speed of switching, the lower on resistance, but also there's some other properties like the ability to run at higher temperatures that gives SiC a number of benefits over silicon.
Yeah. So if you think about higher temperatures, a couple things you can do. You can push the device harder in switching frequency, generate more heat compared to a silicon device, or you can do things like remove some of the heat sink. So you can go to a smaller heat sink, or maybe you switch from a liquid cooled application to an air cooled application, which cuts the cost, cuts complexity. So, I mean, those are just the immediate ones. And then you look at other applications where the temperatures might be going 175 degrees C or higher. Again, silicon carbide is ideal for those where silicon just won't make it.
So it sounds like actually SiC has got different benefits that apply in different situations. Would that be right?
Yes, that is correct. Silicon carbide has a little bit of advantage in voltage. It's quite radical with the performance of these die, and we're only seeing the first wave really of silicon carbide rolling out. And I say that because the first wave is a silicon device or a silicon die replacing, or a silicon carbide die replacing a silicon die in like packages. So it's the typical put the Ferrari engine in the pickup truck. The pickup truck goes a little faster, but you're not really optimizing the capability of silicon carbide die. And the next wave is now packaging. We're looking at these different types of packaging technology, top side cooled, dual side cooled, that really help with that performance. But that's only on the thermal side. The other area, since we're pushing more the frequency and current, the parasitic inductance in the package is also becoming much more important. So, you're seeing these packages with much lower inductance, which really allows you now to perform at higher levels than what was achievable before. And then ultimately, we're going to see higher voltage. We're seeing 3.3 kV out, 6.5, but silicon carbide has the ability to go much, much higher than that.
That's really exciting. It sounds like there's a lot going on, but Before we dig too much into the future of silicon carbide, let's go back a little bit. I mean, Microchip, most people know Microchip as an MCU vendor. How did Microchip get into SiC?
Yeah, it's another great question. So Microchip acquired Microsemi in 2018, and that's where they got the silicon carbide from. And if I go even back further than that, Microsemi acquired a company called Advanced Power Technology, or APT. And APT has been really pushing silicon carbide for over, back past 20 years. So I think in 2003, they shipped their first device. They were really looking at it from a very strategic standpoint, looking at, hey, if I take this existing silicon IGBT module, maybe I need to reduce the parasitic inductance in the package to get more performance with these silicon carbide diodes. So we've got this heritage, kind of our provenance, that goes way back from APT to Microsemi. And a lot of people say, oh, yeah, we know the Microsemi silicon carbide. And sometimes they don't know the leap from Microsemi to Microchip.
And that heritage is important, isn't it? I mean, people really care about buying from companies that have got a track record in silicon carbide.
Yeah, I mean, it's a different technology, and there's definitely a learning curve. So if you just decide I want to jump into silicon carbide, it's not so easy. Just the starting material itself, how you create a silicon wafer is much different than how you create a silicon carbide wafer. And when you start looking at the processing capability of your fab, there are a lot of, let's say, minor things that you may not be thinking of that are quite important. So having a background in not only, silicon carbide, the materials, properties of it, really going into your design rules and your process capability is really key to optimizing for reliable performance.
That's good to hear. So, I mean, with all this history, do you make SiC products? Because they need a completely different process, don't they, from standard silicon?
Yeah, so we actually have a dual fab strategy where we have our fab in Colorado Springs that does silicon carbide. We also use a foundry. What that does is help de-risk, any kind of supply chain issues, but that also means we own the technology and the processing as opposed to being reliant on a foundry.
And that Colorado facility, I mean, is that something you've just got through acquisition, or is that a facility that Microchip is continuing to invest money in?
Yeah, so that was through an acquisition. And earlier this year, we released a press release indicating, we're putting $880 million into that facility to expand its capability. So silicon carbide is important to Microchip, as demonstrated by their investment. We see a lot of future for this technology way beyond where we are today.
That's an impressive investment, actually. That shows a lot of commitment and confidence in SiC going forward. I mean, one of the things I've heard is that engineers who design with SiC for the first time, they find it can be a bit challenging. It's not the same as silicon. So, what are the biggest challenges engineers have when they're designing with silicon carbide? And is there anything Microchip is doing to make that easier for them?
Yeah, I mean, I would say the biggest challenge most people face is the fast switching of silicon carbide devices. It usually manifests itself in EMI or rigging in the circuit. And this is something that requires, a skill set, but also we're seeing different technologies that can kind of mitigate some of these challenges. For instance, we've got this digital gate drive technology. It's a patented technology unique to Microchip. And unlike let's say, traditional gate drive, which uses a gate resistor to charge and discharge gate capacitance. So think of it as just as an RC time constant. We can step the voltage for turn on and turn off. And what that does is that tailors the performance of the turn on and turn off. And in turn off, ideally what you want to do is as you turn off, go discharge your gate source capacitance, really drop down to the Miller plateau very quickly. And then you can do a couple things. You can hold a little bit and then turn off. And what we found is when you do that, you can actually reduce some of your switching loss. So you can make the application more efficient. But if your challenge is more like rigging in the circuit, you can hold a little bit longer. And what you're doing is you're trading off some of that energy in the rigging to the turnoff energy. So your turnoff losses go up, but all your rigging comes way down. And that means maybe you can eliminate some of your snubbers or your filtering needed for that ringing.
And that's interesting. And presumably, some of the other things you're doing is to reduce inductance, as you mentioned before. Is that also to help reduce the ringing and allow for faster switching speeds?
Yeah, I mean, reducing the inductance does a couple of things. One, it allows you to push it to a higher switching speed, but also can reduce the overshoot. So we've got a package that's down to 2.9 nanohenries, and that allows you really to push, ideally more current through it, because if your overshoot's less, you have to worry less about that overvoltage.
And you mentioned some other things happening in packages around cooling. So do you want to talk a little bit more in detail about some of the things you're doing with double-sided cooling and other approaches to, reduce the size and make the SiC solution more efficient?
Yeah, we're seeing more and more people looking at double-sided cooled packages, mainly surface mount type. As the whole industry comes up, this is what's driving some of these adoptions. So originally, I said, it's the SiC die in the existing SiC silicon package, and people are used to that. But now they're looking at, oh, I want to get more size out. I want to get more power out. What I always heard was twice the power and half the space. So how do you do that? Getting more power through the existing device, going to higher frequencies. All that means you're going to generate more heat in a more confined area. So this is where these other technologies really are starting to now become more mainstream. People are becoming more comfortable with these type of cooling methods. Before, they were just using as big a heat sink as possible. And sometimes it was looking at modules versus discretes and looking at your power budget. In some cases, you can really take a module and take a discrete version of that module and spread your heat out more. Now it becomes bigger, but there's the trade-off. When you look at your application, what are the things that are most important?
And that's interesting. I mean, you talk about modules. Microchip's actually manufacturing SiC modules. Is that something you really believe is in the future? I mean, after all, you're a semiconductor company and not a module manufacturer, aren't you?
Well, we are a module manufacturer. We actually design and manufacture the modules. And by doing that ourselves, it helps us optimize the whole solution. We want to be agnostic to the customer, whether they want to have a discrete solution, a module solution. Typically, what we see as the power levels go up, people like the integration in the module. It's easier if you think of paralleling these die in the module versus paralleling discretely. There are customers that do want to parallel discretely. By large amount, the customers are going more toward the modules for the higher power.
And presumably, I mean, a big thing about the modules is just that ease of use. It means that there are fewer problems, fewer challenges. And whilst you might not get that absolute smallest size you could with double-sided cooling, it's going to be easier to design in. Is that right?
Yeah, I mean, and one of our most popular is the SP6Li. That's our low inductance power module. This is the one with 2.9 nanohenries of parasitic inductance. And ideally, we're seeing people just take those, strap them onto heat sinks. We have a digital gate driver, just literally goes right on top, and pretty much they have the power stage right at that point.
And that 2.9 nanohenries, I mean, that sounds low to me, but how does that compare to other solutions in the market?
Yeah, I believe it is pretty much the lowest of any commercially available module out there.
So that's pretty awesome. So here we have you guys, normally a semiconductor company, but you're developing industry leading modules as well. That's really cool.
Yeah, we do have a good expertise in modules, both standard, what we call derivatives. So let's say you like this module, but you want a different base plate or different types of terminals on it. That's something that we definitely entertain. We're very good at doing those derivative products. And we can also do a full custom. I mean, we've got these hybrid power modules with multiple types of chips in them. So we're trying to position ourselves as the full capability of Microchip, not just on the silicon carbide side, but pulling through all the other capabilities Microchip has.
That's fascinating. I mean, it sounds like you're working on this whole complete solution. I mean, one of the other things Microchip talks about a lot is reliability and ruggedness. And I guess this is because, SiC had a reputation in the early days of maybe being not quite so reliable. Can you explain what's happened and how SiC has now become, a technology people can trust and that has a long lifetime and how you've achieved that?
Yeah, good question. A lot of our competition wants to know the same thing. But yeah, there were some challenges originally when some of the silicon carbide MOSFETs or JFETs came out. And some of those reliability concerns have been addressed to the point where the market is adopting silicon carbide as, an acceptable product. And we've always focused on the ruggedness and reliability of our products. And We've benchmarked ourselves. We've had universities and other outside sources benchmark us. So the gate oxide is pretty much the weakest part of the MOSFET. And we've evaluated our gate oxide integrity by doing these, they're well documented, accelerated stress tests. So you basically test out the oxide, you do some testing to it, and then you test it again to failure to see, did it weaken? We have over 100 years of operation if the junction temperature is 175. So if you're running cooler, it's going to be even more. So for us, the oxide is not an issue. It's rock solid as well as our voltage thresholds. They're not changing over time due to the stress, which is really critical. The other thing is the actual body diode in the MOSFET itself. Ours is very robust, meaning you could actually run current through it in the forward direction. And what happens on some of the other suppliers' products is that will start to degrade the MOSFET performance over time. You'll start seeing the IV curves start to go down more and more and more. This was done actually by a university, not by us, but ours was just rock solid, repeatable every single time. And then there's what's called avalanche. So avalanche is when the voltage exceeds the voltage capability of the device. It can't withstand that. So basically it avalanches and current goes through the body diode in the reverse direction. We've tested ours with 100,000 pulses. And again, no degradation. So what does that mean? Typically, when you have a device that you can't do that to, you have to put a freewheeling diode in line with it or a snubber to protect it. You don't need to do that with ours. And in some cases, we've actually seen people replace 3 competitors' modules with 2 of ours. And another reason they can do that is we also have a very flat RDS on curve, meaning as the temperature goes up, your RDS on goes up too. Our temperature coefficient is much flatter than the competition. So at 25 degrees C, everyone rates their module, let's say at the same RDS on. As the temperature goes up, theirs goes up to a higher resistance, meaning less current will go through. So then I need more modules or I need more heat sinking to accommodate that. So this ruggedness and reliability really ends up providing ideally the lowest system cost for our customers.
I love that. The ruggedness and reliability ultimately is a cost reduction for customers. I think it's a great way to think about it. I mean, one of the things I've learned doing this podcast series is Microchip's very focused on total system solutions. So can you talk a little bit about how you work with some of the other business units in Microchip to develop, system solutions around the SiC products?
Yes, we've got some reference designs. We've worked with some of our, let's say, sister business units, the MCU groups. We have a Vienna rectifier. We have DC to DC converters. Ideally, our advantage is we could provide a total system solution to a customer, meaning they don't have to work with multiple suppliers. They can work with one supplier, and that one simplifies it for them, makes their sourcing a lot easier. But also when there's troubleshooting, typically what happens is, someone comes in, no, it's not my device, it's the other guy's device. You take that right off the board. We work very closely with our customers to get them to market as quick as possible.
That's great. Perry, this has been a fascinating sort of, overview of what Microchip is doing in silicon carbide. I mean, before we go, I'm interested, do you have one piece of engineering advice you'd give to the listeners?
Gee, that's a good question. I think we see a lot of people transitioning already from silicon IGBTs to silicon carbide. And you asked the question about what's the biggest challenge, EMI, ringing. Our digital control makes it so much easier for them. I think we looked at it and we looked at doing a ground up design, going through all the permutations of changing your gate resistor to tune your circuit. You don't have to do that with the digital control. It's all through keystrokes. It's like a 6-month savings in time to market. So when we show our products and our portfolio customers, they typically say, there's 2 things we want. We want a sample of your SP6LI, that very low inductance package, and we want your digital gate driver that goes with it. So we actually sell a kit that has them both because it's just such a popular thing. It's called a NASDAQ Plus kit. Literally, you can strap 3 of those on a heatsink and you pretty much have your inverter right there. So if you're looking to get to market with SiC very quickly, that's one thing that we're really focused on.
That's awesome. I mean, we've talked about so much. Is there one thing you'd like people to take away and remember about Microchip silicon carbide?
Yeah, there is, that we have it. Our biggest challenge, you kind of hit it, was most people think of Microchip, MCU controller company. Microchip's been very, very successful at positioning themselves, a leadership role in that. With the Microsemi acquisition, we do have silicon carbide. And, one of the things I find very often when I ask the salespeople, and that's whether it's a Microchip salesperson, one of our channel partners, how did you get this success? They say, I ask, did you know Microchip has SiC? And they say, no. Well, they've got this great, rugged, reliable SiC. They're very impressed, turns into a design win, and literally happens about that quick.
That's awesome. And a very easy thing for listeners to remember. I mean, we covered silicon carbide very briefly, and I think just touched the surface. If anyone's listening and they'd like to find out more about Microchip silicon carbide, or indeed ask you some questions, what would be the best way to get in contact, Perry?
Yeah, so we try to make it easy. If you want to find out about Microchip SiC, it's really microchip.com/SiC. It's a single portal. Everything we have is available based on silicon carbide through that portal. Me personally, if you'd like to contact me directly, it's perry.schugart@microchip.com.
That's awesome. Perry, it's been fascinating. I really appreciate your time. Thanks so much for being on the podcast.
Thanks, Mike. It was great being here.
Thanks for listening to the Microchip Is podcast. Please follow us on your favorite podcast platform to keep learning about the many technologies, products, and people that make Microchip what it is today. Look out for our upcoming Microchip Is podcasts and our new Beyond the Microchip podcast series.